Today I will talk about our work on formal verification for trustworthy human-robot collaboration. Human-robot collaborative systems plays an important role in our society, and it has many applications such as autonomous driving and social robotics. However, to ensure the safety and trustworthiness of this type of systems are quite challenging. The first challenge comes from the different sources of uncertainties, such as the quantifiable sensing and actuation errors from the robot, the unquantifiable human behavior, as well as the unknown or dynamic environment. And the second challenge comes from the complex requirements and constraints for this type of systems, such as safety, task and constraint satisfaction, and robustness. To tackle these challenges, our proposed framework is as follows. First, we propose to abstract this type of systems using probabilistic modeling, such as partially observable Markov decision process or uncertain MDP, to take into account different sources of uncertainty. Moreover, for the desired properties of the human-robot collaborative system, such as safety, constraint satisfaction, and robustness, we propose to concisely express them using temporal logic. Such as linear temporal logic or linear distribution temporal logic. Once we have the model and the specification, we study the verification problem, which aim to develop algorithms for proving model satisfies specification. We also study the synthesis problem, which aims to design algorithms for devising policies from specification. The first problem we study is trustworthy human-robot collaboration. Let's see this figure as an example. Here we consider the route planning problem for autonomous driving. Well, there is a vehicle driving in the city, and for each road segment, there are different types of incidents, such as a pedestrian crossing the road, an oncoming truck, or obstacles on the road. Depending on the human's trust to the vehicle, as well as the difficulty in handling these road incidents, the human can choose between autonomous driving mode or manual driving mode. As you can see, the human's trust plays an important role for effective human-robot collaboration. And since human's trust is not observable to the vehicle, we propose to use trust POMDP as the modeling framework. Here, X is the robot state, AR is the robot action, and theta is the human trust, while the human trust is not observable. For observation, we consider a triple, while ID is incident, which can be intuitively understood as a set of events that will affect humans' behavior and humans' trust. And AH is the human action, and ER is the robot performance. A POMDP policy is defined as a map from the robot state and the belief state of the human trust to the robot action. To further complement the model, we propose data-driven learning approach, where we first connect data online, which was then used to train a trust dynamic model and a human decision model. Then we further consider the safe planning problem for the robotic systems among dynamic agents. Well, we consider an unknown environment that is populated with unknown dynamic agents. Well, the purpose is to guarantee the safe operation of the robotic systems. Here, the robot is modeled as a POMDP-M. For the unknown dynamic agents, such as pedestrians, the proposed idea is as follows. First, we train a neural network-based predictor for predicting the future trajectory of the dynamic agents. Moreover, adaptive conformal prediction is further used for uncertainty quantification. For instance, in this figure, the blue dots are the history trajectory of the pedestrian, and the red dots are the predicted future trajectory of the pedestrian, while the red circles are the prediction regions constructed using the adaptive conformal prediction. In addition to the collaborative scenarios, we also consider non-collaborative human-robot interaction, such as the human and the robot are playing a game. In this case, we need to handle quantifiable uncertainty, such as robot actuation errors, as well as unquantifiable uncertainty, such as the unpredictable human intentions. In this case, we propose to model the human-robot interaction using Markov decision process with set-valued transitions. Here, the Here, the probabilistic transition function is set-valued rather than single-valued, while the set-valued target states can be used to capture unquantifiable uncertainty. Here, due to time constraints, I will not go to the detail of this work. Okay, now let's see how to specify the desired behavior of our systems. Here, we propose to use linear temporal logic or linear distribution temporal logic. The differences between the two is that in linear distribution temporal logic, we consider both state predicates and the belief predicates. The state predicates is associated with the states, while the belief predicates is defined over the belief space and can be used to capture constraints that are defined over hidden states. Okay, now let's see some example of properties that can be captured using LTL or LDTL. The first one is safety, which is quite simple and can be expressed as a LTL formula. And the second one is the route planning with human trust constraints. Here in this formula, GJL are three state predicates which correspond to three road intersections in the previous map. And the high trust and the low trust are two belief predicates that are defined over the unobservable human trust space. We can also consider repetitive tasks such as persistent assembly and delivery. Once we have the model and the specification, we can then study the verification or synthesis problem. And the solution is summarized in this figure. First, given the human-robot collaborative systems and the interaction relation between the human and the robot, we can abstract the system using POM-DP or MDP-ST. And then we express the desired behavior of the system using linear temporal logic or linear distribution temporal logic, which is then further translated into a limit deterministic Booking automata or deterministic finite automata. Then we build a product between our model and the automata translation of the formula to obtain the product POM-DP or MDP-ST. Then over the product POM-DP or MDP-ST, we can design an algorithm to obtain the optimal policy. Notice that when there are unknown dynamic agents in the environment, we further apply neural network predictor and adaptive conformal prediction for constructing a set of prediction regions. These regions are then used for constructing a safety shield. One can then integrate safety shield with the optimal policy synthesis algorithm for guarantee safety. We formally show that our algorithms are correct and can provide at least probabilistic safety guarantee. Now let's see some experimental results. First, we consider the route planning problem for autonomous vehicles as we've seen before. In this case, we hire in total 22 participants from the university campus. And for each participant, they are required to sit in front of a monitor and a driving wheel. Here on the monitor, we create an environment using color, and then the participants can choose between autonomous driving mode or manual driving mode using the button on the driving wheel. And he can also increase or decrease his or her trust in real time. Okay, now let's see a video. And this video shows how the human's trust level increase or decrease when seeing different road incidents. You can also see how the human switches between autopilot mode and the manual driving mode. Finally, let's see this table, which summarizes the experimental results. For each participant, we asked them to drive two routes. One is trust-based and one is trust-free, which is basically the shortest path. And you can see that the trust-based policy outperforms the trust-free one in terms of the satisfaction rate for the temporal formula as well as the average trust. We also conduct experiment for the safe online planning problem. Here we consider real-world pedestrian trajectory from benchmark datasets. We consider a failure rate delta equals to 0.05, meaning that we must guarantee a safety of at least 95%. We consider three scenarios: ETH, hotel, and New York Central Station. Let's see the results in this table. Here, the shielding with ACP is our algorithm. We also consider another two base algorithm. The first one is no shield, and the second one is shielding without ACP. First, let's see the safety rate. You can see that our algorithm gives the highest safety rate in all scenarios. Moreover, let's also have a look at this parameter m, which is the number of dynamic agents that we consider at the same time. And you can see that our algorithm can take into account hundreds of pedestrians at the same time without increasing too much of the computation time. Okay, now let me summarize our work. Here I record this figure that you've seen before, which demonstrates the framework of our approach. And finally, I want to thank all my collaborators. Thank you.
Question for Pian.
Hello.
Hi.
Hello, hello. Can you hear me?
Yes, we can. Thank you. I'm
Great.
just trying to see if anybody has questions. If not, I have one. A common criticism we get kind of when we think about formal methods is scalability. And when you think about POMDPs, that's also a very usual criticism we get is scalability. So can you talk a little bit about that in the context of your work? Because you're kind of looking at both things at the same time.
Yes. So yeah, I know that for POMDP, scalability is an issue because we know that when the sorry, because I hear two voice of my.
We can hear you well. I don't.
Okay. I just continue. So, in our case, because we know that to solve POMDP is a really difficult problem. So in our approach, we basically using online planning algorithm like partially observable Monte Carlo planning, which is known to be quite efficient for large-scale POMDPs. For instance, for the case of safe online planning, basically our approach contains three algorithms. The first one is to using neural network predictor and adaptive conformal prediction to construct a sequence of prediction horizons for all the dynamic agents. And then we use this information to, on the fly, constructing a safety shield. And then we integrate POMCP with this shielding technique to guarantee safe operation of the robotic systems. And in our experiments, we see that our algorithm actually is quite efficient for different scenarios, and some are small and some are actually quite large.
Okay, we're running a little late, so I think we'll keep it at that. Thank you so much, Pian. Thanks to all the speakers, and we conclude our sessions. Thanks, everyone.